ठीक है, fine. I am starting.
Right now, I can see there are about 80 participants have joined.
80.
80, sir.
Good. Fantastic. Okay.
And we have the PhD scholars. They all are sitting here.
Okay.
At
Absolutely.
MIT Jaipur.
ठीक है. Just let me say यार, मैं सुबह डाउनलोड करके रखा था. और एवरी टाइम वही प्रॉब्लम होता है. Well, let me say there is some. It's now visible?
Yes, sir. It is visible, sir.
Okay. So very good afternoon to all of you.
Full screen, sir.
Eh?
Full screen, sir.
It is showing full screen to me.
Okay.
F5. Let's see. फुल स्क्रीन नहीं आ रहा है
सर. फुल स्क्रीन तो नहीं आ रहा है.
विजिबल हो रहा है ना?
हाँ सर, चलेगा सर.
ठीक है, लेट मी स्टार्ट. क्योंकि अच्छा पहले मेरे को बता दो, स्लाइड मूव कर रहा है अभी?
हाँ सर, स्लाइड मूव कर रहा है सर.
लेट मी स्टार्ट.
ठीक है सर.
Very good afternoon to all of you. So today I will talk about the multi-objective optimization. I hope till now you have already got some idea regarding this single objective optimization. So when you are talking of any optimization technique, whether it is single objective or multi-objective, there are two basic things. One is the unconstrained optimization and another is the constraint optimization. So the question is, when there are certain constraints are there, then there are different methodology how to handle this constraint in the evolutionary computing domain or in the swarm intelligence domain. Because there what will happen, these constraints are to be evaluated, and based on the deviation of those constraints, then the fitness function will get some penalty. So that's why anybody working on this, whether it is a single objective optimization problem or it is a multi-objective optimization problem, you have to look into different constraint handling methods and the penalty which we are giving, and you must be very clear between the objective function and fitness function. So generally we evaluate the fitness function. So fitness function is basically, if it is unconstrained, this is objective function. If it is a constraint, then objective function plus some penalty. This plus or minus, that depends on what exactly you are doing, that I have told in my first class. Now let us talk about some of the multi-objective optimization. So in real life scenario, there are multiple optimization which comes up the multi-objective. Although we are talking of multi, after there is another research domain which evolves after this multi-objective, there are many objectives. So the question is, the way multi-objective optimization has been decided a priori, I'm just talking to that. Then we'll go to the many. So some real world problem, for example, if you want to find out a product whose cost is minimum, because somebody want to purchase that. So you can see there are so many objectives. Minimize the cost of the product. Then simultaneously you want the cost is minimum, but the quality of the product must be good. Maximize the quality of the product. Minimize the wastage of raw material. Minimize the efficient use of the machine and the workers. That means efficient use of the man and machine. So now you see, these are the four objectives. You can look into, if you are minimizing the cost of the product, that can be achieved by minimization of the waste of raw material. That can be achieved by maximizing the efficient use of the man and machine. So if you look into the objective 1, objective 3, objective 4, they move in the same direction. But if we look into the objective 2, maximize the quality of the product, this moves in the opposite direction. You cannot have a best product with a minimum cost. You cannot have a worst product with maximum cost. So my point is try to understand what exactly I am trying to tell all of you. You have to find out the objective which move in opposite direction. Okay, so they are conflicting objectives. If you want to achieve one objective, the other objective has to be go down. For example, I will give some example. Definitely, this is one example. If you want to purchase a car, you want the cost of the car should be minimum. But simultaneously, as a user, I want the comfort I will get by that car is maximum. You can't get it. You have to go with a minimum cost, whatever vehicle are, they are in the range of 5 lakh, 6 lakh, 7 lakh. So it is a minimum cost. You may not get maximum comfort or maximum quality of the product. But if you go, the cost of the car is 50 lakh, 60 lakh, like that, or crore, then definitely the comfort is maximum. So cost maximum, comfort maximum, cost minimum, comfort minimum. But if you want to have a solution which will minimize the cost and maximize the quality or the comfort in that particular, that is, these two are known as contradictory objective, where we talk about this multi-objective optimization. Now, how can I mathematically formulate? You know that there are n number of variables in your problem. Now you have to minimize or maximize f. Now, instead of this function, a single function, there are multiple functions, f1, f2, up to fm. Some of the function, they move in the same direction. You can have two groups of the function, let us. Okay. Subjected to some equality constraint, that is, every variable x is a vector. There are n number of variables in that objective function. So that these are the equality constraint. Every variable is having its lower limit and upper limit. Then there are some inequality constraints also. 5x1 plus 3x2 is less than equal to 0 or something like that. So these are the constraints. Now the question here is how to optimize several functions at a time, at once, if there are more than one objective. So one way, I'm giving the difference between the single objective and multi-objective. Single objective, you have to optimize only one objective function. In multi-objective, you have to optimize more than one, two, or more than two functions. So in case of a single, we will get a single optimal solution. But in the multi-objective optimization, I need a set of optimal solution instead of a single solution. Okay. And the maximum and minimum fitness value is selected as the best solution in single objective. But here we have to compare the solution. I'll come to that later on. Now let us see here two different functions. Very easy to understand. What happens if I plot the function f1? F1x is x square, and the range of x is minus 10 to 20. Now x square is basically, now you see x is minus 10, that is 100, x is 20, that is 400, x is 0, the value is 0. So you are getting the red curve. So the function 1 is the red curve. Function 2, f2x, x minus 10 whole square. That means when x is minus 10, this starts from this. So minus 10 is minus 20, minus 20 square is 400. When x is 10, this becomes 0 and it goes on. So now please try to understand, these are the, when one function is maximum, not necessarily the other is also maximum. Okay, because minus 10, this is maximum. If we will take now these two simultaneously, I want maximize this and maximize that, then you have to find an optimal solution. So that is the way generally the function they converted to from the x is the variable with respect to fx. So you can plot function 1, you can plot function 2 in different figures or one figure. Now I'm transferring this function to another space that I want to plot f1 versus f2. Now you see, when f1 is 100, what is the value of f2 at that time? This is 400. Okay, for minus 10. So if you plot f1 minus f2, you will get another set of corpse. So that's why that is the thing we want to find out later on. The how this is achieved. If we want to suppose there are two objective function f1x, one objective, and f2x in another objective. So generally in mathematics, what the people do, they take a weighted average. You formulate the fitness function. The fitness function is some weightage to objective 1 and some weightage to objective 2. And these weightage are normalized so that W1 plus W2 is becomes equal to 1. You may give 10% weightage to F1 and 90% weightage to F2. So if somebody now try to understand my point, what exactly I'm telling. So now the multi-objective problem with assigning some weightage to each objective is converted to a single objective problem. And you solve this single objective problem by already discussed methods, whether it is GA, whether it is PSO, whether it is a differential evolution, or whatever the algorithm. Okay, but here you will get only one solution, and that solution is purely dependent on the weight. So what will happen? I may solve it by taking 1% to F1 and 99% to F2. I will get one solution. Somebody may give W1 is 2% and W2 is 98%. So in that case, how many solutions you are getting? You are getting 100 solutions. Okay. So 100 solutions are there by giving different weightage to each function. And it may happen sometime for a particular weight combination W1 and W2, the solution may not exist. So that's why the limitation of conversion of the multi-objective optimization to a single objective optimization is the result is purely dependent on the weight, and you have to run the algorithm multiple times. You change the weight, run the algorithm, change the weight, run the algorithm. So multiple run of the algorithm are required to get the whole picture of all the 100 solutions, and it is very difficult also to select the weight. For example, if I want to minimize the cost of the product, so cost of the product is expressed either in rupees or in dollar or in pound or something. And simultaneously, I want the comfort level. How will you measure the comfort? There is no. So my point is the F1 and F2 are having two different scales. Then you need a scale factor. Let me give a classic example in electrical engineering. What people do in electrical engineering, we want to minimize the cost of the power production. So when you want to minimize the cost of the power production by thermal generator, the thermal generator burns coal. So I want to minimize the cost of the power production. That means I want to minimize the cost of the coal. So you take the quality of the coal, which is not that much good. So you burn it, you make the power, so your cost is decreased. But simultaneously, because of the lower quality of the coal, the emission of SOx and NOx is large. So that means cost of the power production is reduced, but emission is increasing. If we will go on increasing the quality of the coal, then cost of the power production will increase and emission will decrease. But I want simultaneously a cost should be minimized and emission also to be minimized. I can't get it. And here the cost in terms of the rupees or dollar or pound, whatever I told, and the emission is in terms of the tons per this much tons to produce 1 megawatt power. Okay, so now that ton to convert to dollar, to convert to pound, to convert to rupees depend on different countries. Suppose we are a developing country, there is already a developed country where there is you can't have this much of production, a large penalty. So my point, what I want to drive out here in converting the multi-objective optimization to a single objective optimization, the challenges are the result is weight dependent. Number one, may not be the solution is reached for certain set of weight. You have to run the algorithm multiple times, and it is very difficult to find out the conversion factor as the scales are different. I hope you understand the point. Hence, some as the objectives are non-commensurable, that is, they measure different aspect of the quality of a solution. So we need to tackle this multi-objective optimization problem in another way. So that is the solution we want to discuss. There are epsilon constraint method, which is proposed by Hemesh et al. So you just keep just one objective you keep, and the restricting rest of the objectives they can use the special epsilon value, specific value. I'm not simple here. You can see if you are taking epsilon 1 and epsilon 2, you are getting a solution here, another solution here. These are the because I'm pointing f1 and f2 are the two space. So these are the advantage and disadvantage of this particular algorithm. So what exactly we want? We want a Pareto optimal solution. This slide, it is proposed by Professor Dev Kalyan Mohadev, who was earlier in Kanpur, IIT Kanpur, and the lab which he has developed is known as Kanpur Genetic Algorithm Laboratory, KANGAL. So now you understand that you have two variable letters, x1 and x2. In that x1, x2, you plot your functions, and if you transfer this corresponding value of x1, and this color shows that this is the, because if you take x1, x2, the whole square is a feasible solution. But the feasible solution space is like this. Okay, if this is the feasible solution, every point having a certain value of x1, x2, where you are seeing my cursor. Now here we have taken suppose one solution here, x1, x2. Now you convert the corresponding value to f1x versus f2. Now that point is A. Similarly, another point is here x1, x2 is converted to a point B. Another point C is converted to C. Similarly, all the points, feasible points, because any point lies on the shaded area on the left hand side, that is the variable space x1 and x2, is converted to another objective space, that is f1 versus f2. You want to minimize f1 and you want to minimize f2. So you can see both these spaces. But the question is, although these are the feasible objective space, but not all point will satisfy your f1 and f2 is minimum. Okay, so that's why the major concern here, the first point when you are doing a multi-objective optimization, the first thing you have to do from the space, variable space of x1, x2, x3 up to xn, it is easy to visualize two dimension x1 and x2, but it's very difficult to visualize the n dimension. So that's why this is the classic example of x1 and x2, which is adapted from Professor Dev et al. You convert it to f1x and f2x. Okay, so now what I'm talking about, you will get now the feasible search space. In this space, you can see in this particular point, this is the feasible solution. The red one is the feasible solution in the search space. Okay. Similarly, here you can see if this is the feasible solution by means of this is the convex optimization, Pareto optimal, and sometimes happens the feasible solution also looks like this, which is a non-convex surface. So that is the surface in this case. So now it comes to the Pareto optimality. I'll talk about what is Pareto optimality. Now look into this particular example. Then you can understand all these things. Now, once you are converting all the points on the solutions on the variable space x1, x2 to f1, f2, and I have shown it by ABC earlier here, ABC. Now let us come to this particular diagram. Let us A is a solution and B is a solution. If you want to maximize f2 and simultaneously maximize f1, now you compare the two solutions A and B. Okay. So if you compare A and B, you can see A, this point A is better than B with respect to objective 1 because that is the maximum. And similarly, A is better than B with respect to objective 2. So if you look into the objective space, you are given two solutions A and B. Which one you choose? You will definitely choose A, and B is completely discarded. So I can tell here that is the concept of the dominance. The solution A in the objective space dominates the solution B with respect to objective 1 as well as with respect to objective 2. But the same case will be reverse. If you want to minimize fx and minimize f1 and minimize f2, if it is a minimization, then B having a minimum value with respect to A in f1 domain as well as B is having a minimum value with respect to A. So if it is a minimization problem, I can tell B completely dominates A. So this is the concept of dominance. Okay. So if now stick to maximization problem. If it is a maximization, I want to maximize F1 and simultaneously I want to maximize F2. So I can tell that A completely dominates B, or I can tell B is completely dominated by A. So very simple thing, A is better than B. So I can keep A as the solution, the B solution I can discard. So now please try to understand any point here which is resulting to A, this is a feasible value. I can keep it for the multi-objective, but I cannot keep the other. But here the direction is different. Here I can keep B, I can discard A because this is the minimized problem. You see, that's why I want to give you very clear. This is the minimization. So in the minimization, what happens? B is having a minimum value with respect to A in both the objective 1 and objective 2. So B, I can tell, dominates A. So question is, by means of the dominance, I can select one solution, I can reject the other solution which is completely dominated by the other solution. I hope all of you get the idea of the Pareto dominance. Now come to this. So because you know they're in solution space. So now first point, let us be very clear. You have already discussed about the single objective optimization by GA. So you have chromosome. This chromosome is evaluated. I have told about the particle. Each particle is evaluated for the function. So now let us talk about the multi-objective GA, which we call NSGA, as per Professor Kalyan Mahestep, non-dominated sorting genetic algorithm. Similarly, PSO, the version is MOPSO, multi-objective particle swarm optimization by Carlos A. Coelho. Concept is, if I have 20 chromosomes or if I have 20 particles in a single objective, I am evaluating the function 20 times. But in a multi-objective, for each particle, for each chromosome, you evaluate F1 and F2, plot it. So in F1 and F2, after one iteration, I am getting 20 points. A, B, C, D, E, F, G, like that. There are 20 points. So once one at the end of one iteration, like the traditional genetic algorithm or particle swarm optimization for single objective optimization, you do one iteration. That means you make the movement of the particle or you do crossover and mutation. So initial population have the genetic operators, mutation, crossover, or initial particle, let the particle is updated by the social interaction and self confidence, you are getting new set of particles. So that new set of particles you transfer to the objective function domain F1 and F2. So you will get 20 points. Among those 20 points, you have to perform another subroutine. That subroutine is dominance, the dominance algorithm. Okay. So now in this space F1, F2, I have shown you here three points A, B, C, but here you will get 20 points if you have 20 particles, or if you have 20 chromosomes, or if you have 20 ants, or if you have 20 vectors in differential evolution. So I hope you are clear. Now, once you have that, now you compare the dominance. Now, if I compare A, this is the maximize and maximize. If we'll compare A with respect to B, already done, B is discarded. Similarly, if we'll compare C with respect to B, B is discarded. So B completely now discarded. But now let us compare A and C. You can see A is better than C with respect to objective 2. But A is not better than C with respect to objective 1. So you cannot tell whether A is better or C is better. But with respect to B, you can tell A is better. With respect to B, you can C is better. But when you are comparing the two solutions A and C, these two cannot be comparable because one is better in one objective, the other is better in another objective. So I can tell A and C are non-dominated solution. So I hope out of these 20, you will find some points which are non-dominated. The rest of the points you can discard. Then you perform again your crossover, mutation. So those 20 will give another 20. Now in your basket, that you have to maintain two baskets. One basket is the sorting basket. So out of initial 20, maybe there are non-dominated sorting, only 10 are coming. Now again they go all these genetic operators, they go the particle swarm optimization operators. You are getting another 20 solutions. Again, those 20, here you have 10, total are 30. Those 30 are compared in the dominance approach. Okay, so you go on like this. So ultimately, at the end of 100 iteration or 200 iteration or 500 iteration, you will get a set of non-dominated solution. So please try to understand. This is very uh, easy to implement this particular algorithm from single objective domain to multi-objective domain, but only you are putting another subroutine type of thing which is known as the sorting algorithm. So these are the sorting definition or sorting algorithm: A, B, C, D. So ultimately you can see in F1 and F2 you will get the solution A and you will get the solution D. B and C will be discarded. So the whole solution F1 and F2, this front is known as Pareto front. So the Pareto front consists of a set of non-dominated solution. So in Pareto based non-dominated sorting algorithm, you give, instead of a single solution, a set of non-dominated solution to the user. Okay, so this is the main classic example of this. This is, you see, I want to minimize the cost. So this cost is better. And simultaneously, you want to maximize the comfort, which cannot be. So low cost, low comfort, high cost, high comfort. So instead of giving a single solution to the solution to the user, now the user has to choose a particular solution based upon his or her requirements. Okay, if somebody is having large amount of money, I don't care about the money, I can go this particular solution of the Mercedes or something like that. But if I have a less amount of money, I can go for this. So the classic idea of this multi-objective optimization is you give the user, instead of a single solution, a set of non-dominated solution, and the user has to choose a particular solution based on the requirement. That is known as a particular solution. How you will choose it, that is the decision making. So and the decision making varies from one to other decision maker, because if I am the decision maker to purchase the vehicle for me, I may choose someone, okay, depending on my salary and something, I may go for I-10, I-20 or something like that. So that's why I can't go for this particular solution. So that's why it purely depends on the decision maker which solution is to be chosen. So there are fuzzy based solution, all other type of solution people have approached. I'm giving you, if suppose another example, there are communication people who work in the multi-objective domain. You want to put the sensor network. So when you put the sensor, that means you want the coverage of the sensor should be maximum. The coverage area should be maximum. But to have a better coverage, you have to put more number of sensors. So if you put more number of sensors, then ultimately the cost will be more. So if you want to minimize the cost and simultaneously you want to have a maximum coverage, it's not possible. So that's why this is a classic multi-objective optimization problem. The other optimization problem which we also see day to day is we want to invest the money in the market. It is a basically if you want to put money in the market, you know that if you want to put the money in the market, ultimately having the objective, your return should be more. Yes, there will be a high return, but all the high return are associated with high risk. Low return, low risk. But generally, as an investor, I must get high return with low risk, which is not possible. So that's why these are the point. Then there you have to take decision making. How much money you will put in the fixed deposit, how much money you will put in the liquidity market, and ultimately you want planning to get maximum return in 1 year. So look into your pocket size, look into your income, look your income tax, and all these things you go for saving. So these are the classic way of different problem solving in multi-objective domain. Again, my point is we solve this multi-objective optimization algorithm. And regarding the writing of the algorithm, I hope everybody can write because you have written your single objective optimization for GA, for PSO, for differential evolution, for ant colony. The only thing is, once a set of solution, whether initially generated randomly or in the subsequent iteration after going through evolution process or after going through the swarm intelligence process, you are getting a new sets of solution. So every solution, every set of solution at the end of a particular iteration, again you have to add there, is transferred to another space, that is F1 versus F2. Once it is transferred to F1, F2, the number of solutions you have, that is the population size, is converted to same amount number of point on the function space F1 versus F2. Then among those 20 points, you perform the non-dominated sorting. While perform the non-dominated sorting, some will be rejected and some will be non-dominated with each other. So at the end of, let us, iteration 1, you have 10 non-dominated solution. Then you again go back to your GA or PSO and do the crossover, do the mutation, do the social interaction, all these things. You are getting another 20 solutions. So those 20 solution is again marked to F1 and F2. Earlier you have another 10. Now you have 30. Among those 30, you make the non-dominated setting. Maybe in the second iteration, you are getting someone better than previously, which was better and in the basket. So every time you have to do this non-dominated sorting among all the feasible solutions you have till your 100 iteration or 200 iteration or 300 iteration. So that is the main idea of the multi-objective optimization problem. Sorry. So this is the Pareto dominance, and in the Pareto dominance, we are getting a Pareto front. Okay. So once you are get a Pareto front, and this is basically earlier algorithm. The first one is NSGA, non-dominated sorting generating algorithm. Then it calls SPEA. A stands for SPEA. That is evolutionary algorithm and generated by the Pareto front. Okay, so these are the different algorithms which are strength Pareto evolutionary algorithm, SPEA. So likely you will get a Pareto front of the solution. Now this is the desirable feature. What is the desirable feature? Now you see, for example, you can look into this green one, this green, sorry, uh, this is the Pareto front solution, actual, true Pareto front. But during your algorithm, you are getting a Pareto front of this nature, 0.1, 0.2, 0.3, 4, 5, 6, 7, 8, 9, 10. So if we look into this 10, see, how you tell my multi-objective algorithm is better than the another multi-objective algorithm? Because you have to compare the two algorithms. So when comparison is done, the basic we look into two things. One is the convergence and another is the diversity. So if your algorithm is resulting a Pareto front, which is very close to the true Pareto front. Okay. Now, here many of you may ask me the question, where is the true Pareto front? You see, in single objective and multi-objective optimization, there are certain mathematical functions already described. It has a true Pareto front. So if it has a true Pareto front and you are now developing a new algorithm, you are testing your algorithm on those benchmark functions for which a true Pareto front exists, you run your algorithm and you get a set of solution, you get a Pareto front. If your Pareto front is very closely converged to the true Pareto front, then you can tell you are getting a better convergence. Okay, that means all the solution generated by your own algorithm are lie on the true Pareto front. Diversity is, you see, for example, all these 10 solution may lie a area only in this space. Then in that case, although you are getting a better convergence, they are on the Pareto front, but it is not diverse. It is not among the whole of the Pareto front. They are only concentrated at certain portion of the Pareto front. So to have your multi-objective algorithm that is multi-objective evolutionary algorithm or multi-objective swarm algorithm, whatever, to be better, it must have a better convergence property and it must have a better diversity. Now you may tell me if it's a, or ask me a simple question. Suppose if the particular problem is not, so for example, I am solving the economic load dispatch, the example I have given. In the economic load dispatch, I want to minimize the cost of the power production and simultaneously I want to minimize the cost of emission. I don't have a true Pareto front because systems are different. Okay, then maybe somebody has produced a literature, they having a true Pareto. I am generating my own Pareto. Compare both. If you compare both, you can get which one is better, which one is having a better convergence and better divergence. So please try to understand the, like in the single objective algorithm, you can test the efficacy of your algorithm by running it multiple times. And when you run it multiple times, you find out the standard deviation of the solution. If the standard deviation of the solution is very low, that means you every time you run the algorithm, almost you are getting the same result. That is treated as a better algorithm. And the algorithm has having a better convergence. Every time it is converging to the nearby solution. So similarly here, you must have a better convergence to the true Pareto front and better divergence or diversity throughout the Pareto front. That is the most important thing in the multi-objective algorithm. So these are the two goals of MOEA as I told. You see here, the all these solutions are crowded. In the they must be, instead of crowding, they must be come to the diversity is there. So that is the most important thing. It increases the diversity of the solution. So this method, which is also proposed by Professor Kalyan Medev, is naiching. Okay, naiching and crowding distance. So there are certain strategies to improve the convergence of the Pareto front and to increase the diversity of the solution, like naiching, crowding distance, Pareto ranking, and the elitist strategy. These are the different methodology which are already used. So how to increase the diversity? You can increase the diversity through mutation, pre-selection. There are different crowding model also, which is proposed by De Jong in 1975. So we can have some papers, just get the idea how you can increase the crowding distance, and all these things are very. I'm not going to the sharing function model and this is basically convergence measurement. You see, what happens? You find out some measurement that is known as the GD, because sometimes the reviewer and others ask you, you prove how your algorithm is better. So now I have a Pareto front P dash. That means all the point on the optimal Pareto front is known. If you are finding a solution Q, now you find out how much distance is Q from the P dash. So that's why this is basically the GD is the general distance. You find out the distance I, okay, for a particular Pareto, there are P number of points for one solution to Q number of solution. So this is basically GD equal to I equal to 1 to mod Q. That is the number of solution. You calculate the distance of I, okay, to the power P. P is the number of points on the Pareto, to the power 1 by P. So this is basically the distance. Where is the point and where is the point on the kth, you see, FMK or FM, this FMK is the nth objective function value of the kth member of P star. P star means actual Pareto. So the lesser the value, the better is the performance. That means you have to compare how far you are in both the domain x1 and x2. Okay, that is the m equal to 1 to m. M is the number of variables. Okay, the parameter, number of parameters in that. So you have to find out the convergence matrix. You have to find out the spacing, how the points are spacing. The points are good space, equispaced. That means better divergence. Okay, so this property spacing gives to the divergence, and this one is basically the convergence property. So this is developed by NSGA. You have NSGA, NSGA2, NSGA3, developed by Professor Kalyan Medev, and it is famous for the non-dominated search method. And fitness assignment is basically based on the ranking based, and diversity mechanism is based on crowding distance. It uses the elitism. If you go on studying different literature, you see NSGA, then MOPSO, multi-objective bacteria foraging, people are applying many type of different ultimately the aim, the aim is you have to produce a set of non-dominated solution. That is the most important. This is a problem which generally uh, this slide I took from Professor Panda, and maybe Professor Nanda is having also the same side, just to have a initial population, how it is running, and you can see these points. If you are finding these points, and suppose you are minimizing f2 and minimizing f1, then you can have the only this solution keep this particular one, this particular one, this particular, and this all others are gone. So likely as you go on, you can see the shape of the changing. Okay, so you can get one Pareto like this, the other Pareto might like this, 3, 4, 5, 6 solution can be neglected. So that's why you have to give, my point is you have to give a ranking. You see, the rank 1 is given to all those 4 points which are non-dominated to each other. Even if 10 and this particular this solution and this solution are non-dominated, this is given on rank 2, but others are uh, not dominated by each other, they are given rank. So according to the rank, you can keep on this ultimately solution. So this is a basically crowding distance type of algorithm. You may uh, follow any of the literature on this particular one. I'm not going into this. I will give this you can see this is your initial state of the solution. This is after 10 iteration, but you are not getting, you see, if you are looking after 10 iteration, even if you are getting a Pareto front, but try to understand the Pareto front, although is having the convergence, but it is not having a divergence. Like you are not getting any solution from 0.25 and to up to that. Some points are crowded here, some points are crowded here, and that is going to be better after 20 generation, and after 40 iteration you are getting, and always you are maintaining 10 set of solution, 1 2 3 4 5 6 7 8 9 10. Okay, so that is the important thing of this multi-objective. But the issue are here, the in each generation the non-dominated set is maintained, fitness is adjusted according to the dominance of the each value. That is one of the point, and the diversity you have to increase on that. So this is the first paper which discuss about the non-dominated sorting genetic algorithm by Srinivas and Dev in 1995. Okay, genetic algorithm started in 1975, and after almost 20 years, the concept of non-dominated sorting genetic algorithm for multi-objective has come. And but this website I don't think presently exists because Professor Dev has left IIT Kanpur. And similarly, Professor Carlos Coelho Cinevista, he has also developed yeah, Cinevista.mx Mexico, developed multi-objective evolutionary algorithm, MOEA, multi-objective evolutionary algorithm. So that is also a published book by him in 2002, and some conference proceeding. And from his website, you can find a lot of MOPSO and MO multi-objective PSO and multi-objective evolutionary algorithm, MOEA. I'm giving here another application of this multi-objective optimization, which maybe most of you are doing and most of you are interested. Because point is, somebody may tell, okay, I'll get certain algorithm from somewhere, but I need to find out certain problems. So problems I have already given you. One problem is electrical engineering people do having two objective, like costs of the power and quality of the power. Similarly, communication people, they may look into the placement of the sensor in sensor network for the better coverage, cost is high. Similarly, now people apply neural network. Why you apply neural network? Where you apply neural network? Basically for classification. If you are using it for classification, what is your objective function? The objective function is classification accuracy. The accuracy should be maximum. Or indirectly, you can tell the error should be minimum. Classification error should be minimum. Now, suppose you can see these three. I want to construct a neural network for a classification problem where the number of inputs is 2. The number of output is 1. That is the classification accuracy or error. In this graph, it is error. Now, there is no hard and fast rule. I know one thing. There are 2 input and 1 output. But I don't know how many hidden layer I will take. Now, this is a very simple structure. 1 hidden layer, 2 neuron. This is another structure, one hidden layer, 5 neurons. This is another structure where two hidden layer, 5, 5, 10 neurons. Now you see, as you go on increasing the complexity of the neural network structure, you may get a better generalization capability looking into the data set. Not always. That's why I'm telling. That's why people are now going for deep neural network. You take more number of layers. But ultimately, here what I want, look into your application domain. In your application domain, if error or classification accuracy is important, that means you want very low error, high accuracy. You don't bother about the computational burden. You don't bother about the complexity. Then you can choose this particular network. But if somebody tells, no, I can sacrifice the error to some extent, but I have to take a decision very quickly. So for that, this neural network is helpful where the error is more, but the computational complexity or the algorithm running time is very less. So that's why these are purely dependent on a multi-objective framework in the sense, if you want a complex network, a network structure is much more complex, better to have a better generalization capability, then in that case, you may tell that the complexity is more, but error is reduced. Less complexity neural network, error is more. So depending upon your application domain, if it is a classification, if it is a medical diagnostic problem, I don't bother about the complexity. I don't bother about the running time. I don't bother about the computational burden on my computer. I am only bothering, I must get a high accuracy. So in that case, you may go for such solution. But but if I want a solution which is applicable to a online control problem, like the firing angle of the inverter, the optimal sequence of the firing angle, then in that case, you have to take a decision very quickly where you can sacrifice the error to some extent. You can't wait for a longer time. The whole system may become unstable. So that's why my only submission and advice to all the researchers are, look into your problem, look into the demand of your problem, and accordingly, you can choose a multi-objective application in that particular. Same thing goes for decision tree. In the decision tree, you can see a smaller tree, and these are the more trees. You can have the same error and complexity trade-off, or accuracy and complexity trade-off. So, okay, so you can choose any one from that. So that's why some genetic learning model, you can see you may have a better accuracy in the training, but in the testing data, it may come to another. So this trade-off between accuracy and complexity is very, very important in the case of the neural network learning, or in the case of this type of thing. This is a two objective Pareto front. I have told you this is application area where we have minimized. I want the minimization of the fuel cost, which is dollar per hour or rupees per hour or whatever. And simultaneously, you want to minimize the NOx emission. It is NO2, SO2, etc. So these are the Pareto front which are generated by this particular algorithm. So this is a two objective. You can see cost and NO emission. This is a three objective: fuel cost, NO emission, SO emission, and you will get a Pareto solution like this. Okay, so these are the some application area in the power engineering. People do, I have given this example, economic load dispatch. If anybody from power engineering, you are doing the optimal power flow, you are also do the distributed energy resource placement, like your sensor placement. You are placing the solar, you are placing the wind, and then there are relay coordination, and very simple, the control people, they do PID controller tuning also. To tune the PID controller, okay, you must have this much of within this time the decision has to be taken, the error margin is this. So a lot of application area in this particular. So here I am showing you one another example in another 5-6 minutes, the maximum power point tracking from the solar PV array. Many people do also this type of research. If you look into the solar PV array, now you see this is the voltage of the solar plant, and this is the power of the solar plant. You can see at different insolation level, if the insolation level is 1 kilowatt per meter square, zero 0.9 kilowatt, 0.8 kilowatt, so you are getting this PV core. That means very simple, at a particular voltage, it gives the maximum power. So the maximum power can be obtained from a solar PV array, okay, for a particular voltage level. And likely, if the voltage level as well as the temperature here with solar insolation, here with the temperature. That means the peak power point, MPP, we call it MPP, maximum power point. The maximum power point changes in a solar panel with respect to the voltage, with respect to sorry, the solar insolation, and with respect to the temperature. So now what will happen? Generally, what we do, we design a controller, okay, to this maximum power point. Now you see, if we are operating at 1, you are this voltage and this power. Now pattern 1 around that, increase the voltage a little bit. If the power is increased, then go on moving. Okay. Now suppose you are point 1 here, you increase the voltage, then we'll go to some other point. So this is the right direction. Similarly, here you can see at this particular point, this is your voltage, this is the power. Now this is another voltage, power, this is another voltage and power. So one way it is, so there are 4 cases. One is del P, change in power less than 0, and del V, change in voltage less than 0. Then del P, change in power is, that means you can take negative and positive. Okay, the direction of movement. So this method is known as perturb and observe. You perturb a point, observe what is happening to the power. So likely you can tell this is either a gradient descent algorithm or gradient ascent algorithm, because you have one peak. In the traditional method, I have told you in the first class, x0 plus del x, go on the solution till the slope is 0. So that is the classic method. But what happens? Sometimes because of this is your solar plant module. You can see module 1, 2, 3, 4, 5, then 6. So 5 modules are connected in series, then 4 modules are connected in parallel. So there are 20 modules. So you are getting a voltage, you are getting the current, and you are getting a power. So this is simply PV core. Okay. Now because of the shadowing, if some modules are in a particular, now you see here, you can see 1, 2, 3, 4, 5 in series. So you are getting a voltage across this constant. Then current through it constant. So current becomes now parallel. I1, I2, I3, I4. So here, similarly, if you look into, some of the modules are get partially shaded, then your PV core changes. If this is the module of the PV core, this. Now, whenever you are getting a partial shading condition, then the question is simple. Instead of a single peak, you are getting multiple peak. Now, one peak is here, that is a local peak. Another peak is here, that is another local peak. And one peak is here, that is the global peak. Of course, this is not a multi-objective optimization, but it is a single objective optimization. Gradually, we can make it to the multi-objective framework later on. But my point is, here you need, wherever there are multiple peaks, you need the non-traditional algorithm to track this particular point. So this is one algorithm area where you can see with respect to time. And you see that another important point here, I want to make the problem more complex. As the time goes on, the cloud moves on. That means if you are getting a set of like this, maybe after another 15 minutes, you will get another peak. That means those peaks are changing. So this is a dynamic optimization. Now you see, till now we have no single objective optimization where the peak is constant. The maximum value is constant. The global maximum is constant. It is not changing with respect to time. But here, my global maximum is also changing with time, because which is happening, the shadow, maybe because of a long tree or the cloud, is changing its position. The moment, see the initial position, let us like this, B, and it changes to pattern C. You can see the GMPP, which is here, it has been moved to now the GMPP here. So this is a very classic problem where you can visualize your global value is going on changing with respect to time. For example, I can give you one example when dynamic optimization. This is a dynamic type of optimization. Maybe you are taking the traffic. Now the traffic at this particular time, when the office time, may be maximum at one particular point. But after some time, you are searching the Google map. So the Google map, which will give you the best path in the morning, it may not give you the best path in the afternoon, because the traffic scenario changes. The global peak changes. It may tell you go on this second path. So those are the dynamic type of scenario, dynamic type. So that's why you can see pattern 1, the peak is here. Pattern 2, the peak is here. Pattern 3, the peak is there. So these patterns are changing with respect to time. So you get some idea, practical application of the single objective optimization, the multi-objective optimization, whatever you have already discussed or going on. So these are the some control algorithm, non-traditional algorithm we are using. So uh, for your optimization technique. Similarly, we do something for the solar, for the battery system, because being an electrical engineer, we like. So maybe I'll stop here to take some questions. If you can ask me, then I'll be able to answer. Yes.
So
Uh,
I request all the attendees to put questions in the chat box.
How does handling more than 2-3 conflicting objects in MOO differ from simpler case, and what challenges arise in scenario? You see, I have already shown you with the 3 conflicting objective, because you have to run it in the multi-dimensional space. So that's why you will get it is easy to visualize a 2-dimensional Pareto, 3-dimensional Pareto, but it is very difficult to visualize a multi-dimensional Pareto. But you can handle all those objectives, all those conflicting objectives, to get a dominated solution. Because what I'm doing, I'm transferring the points, a particular point. You see, there are n number of variables, x1 to xn, but that means your variable space is n dimension, but if objective are 2, they are converted to a 2-dimensional f1 f2. But suppose n variable, objectives are 5, they will be converted to f1 f2 f3 f4 f5, and you have to compare a particular solution among all the 5 variable is better than the other. Otherwise all the points are non-dominated at the initial stage. So you can handle it, your algorithm can handle it, absolutely no problem. That is from Amritesh. Any other question, please? Relay, see, relay coordination is single objective, but sometimes what I want a coordination of the relay with minimal change. I don't want, if you will take a distribution system, it is from Giant Money Party. The relay coordination, what we do, every relay, if the primary relay fails, the backup relay should work. But sometimes what happens, because of the penetration of the local generation, the relay coordination changes. Now, my point is, how can I achieve a relay coordination with minimal change in the existing setting of the relay? There we can do a multi-objective optimization. Which optimization is better to solve relay coordination problem? Yes, you can do, because you have to look into the relay coordination is a very tough problem. In the sense that if you are doing a electromechanical relay coordination, then the settings are discrete in nature. If you are making a numerical relay coordination, the settings are a flexible in nature. They can change in terms of 0.01. So absolutely no problem. So that's why you can use any algorithm for the relay coordination paper and problem. You can find some of are done by my group and some are done by others. There are a lot of papers are there. IUC tells, can we use fractional programming problem to model conflicting objects of maximum and minimum type and use this type of algorithm? I hope so. I'm not sure. Sorry, I'm not sure about that, because I'm not worked on fractional programming till now. Okay. See, when you are developing any of your algorithm, Amritesh's question, when you are developing your own algorithm, to test your own algorithm, you have to test it on the benchmark problem, because there are already n number of algorithms which are developed. So if you want to prove your algorithm is better than the existing algorithm, then the ultimate way is to test it on the standard benchmark problem. So that is the important thing. Otherwise, that's why I give you an example. If it is a practical application, there is no benchmarking. Maybe your solution is better than the other. So you take the existing paper, their Pareto solution, your Pareto solution, compare between these two. But if the true Pareto, in that case, you can assume yours is the true Pareto, the other one is the other one. But if the true Pareto exists for the function in the benchmark function, so benchmark function always helps us in improving my algorithm. That is the most important thing. Yeah.
एक मिनट बोलना है।
Anything else? Okay then. Thank you, Professor Nanda.
Sir, uh, yeah, sir, some more questions are there.
It is okay. Sir, in some paper, IGD is used instead of GD. That is yes.
Yes,
But there are much more modifications have done in the most of the thing because GD is initially proposed by Professor Dev.
sir.
Yes.
Yes. Sir, as no more further questions are